Okay, last video here, last example. So in this case, we're going to talk about a concave or a diverging lens. A concave lens is one that looks like this. And what happens is light is spread out from it like so. So they diverge, these rays, as opposed to focusing them together. Some glasses are like that. Some people need the light to be spread out a little bit in order for their eye to focus it. But most of the time we talk about convex lenses. So that's certainly what you mostly think of when you think of a lens. Concave, I remember it being called concave. This is the type because the arc here caves in. And so again, that's how I remember what type we're talking about. So concave lens or diverging lens in this case. So in this example, 1.5 centimeter object is placed 6 centimeters from a concave lens with a focal length of 2 centimeters. What is the size of the image and how far away is the image? So once again, our height of the object or the size of the object, whatever it is 1.5 centimeters in reality. We place it a distance away of 6 centimeters from the lens, and this lens has a focal length of 2 centimeters. But because the light doesn't actually focus at the focal length here, basically you can trace these backwards, with dotted lines here to the point in the back. Concave lenses or diverging lenses, you always use a minus for the focal length. So that's a big difference between the other two examples. So the other two examples, it was positive always. In this case, it's negative always. And so that'll do some differences to make our math work out, and we'll see what happens there. So we're looking for the height of the image, and we're looking for the distance of the image as before. Ray diagram, not too different. You draw the principal plane, and you want to draw your lens somewhere in the center here. And again, it doesn't matter how accurately you draw this. Something like so. In the last example, in video 2, when I drew my convex lens, I called it a diverging lens, which was a mistake. This is a diverging lens. The convex lens is always a converging lens, so that's a mistake from before. So go back and watch that video and find the mistake there. So we have this set up. Again, doesn't have to be completely symmetric, although in reality it should be. And so I want to put my focal length. I'm going to guess something around here, and here is 2 centimeters, and we will call 6 centimeters away about here for my object. Now remember that this is just for example purposes of showing you how to draw these ray diagrams, not to actually do it right. If we were doing it right, we would measure out 2 centimeters and 2 centimeters and 6 centimeters and all these things that we have. And then when we draw our diagram with the lines properly, we would get actually the height of the image and the distance from wherever things end up. You could use the ruler to figure out these things, which should match the math. You will do some of that in the homework, but this again is just to show you how to draw the pictures, and I'm trying to keep these as short as I can. So again, these don't hurt though either, because how this ends up, if the image ends up here or here, that tells you something about if your math is right as well. So it's a representation, but it's not 100% accurate here. So how do you draw these ones? So first off is you start at the head of the arrow here, and you make a parallel line to the lens. And instead, though, of it being focused to the focal length on this side, because this is a diverging lens, it spreads out. Well, where does it spread out to? This way, this way? Well, we know that the focal length is an important spot around the lens, because a parallel line will be diverged away from the focal length in this case. So that'll look something like this, and you get that in there. But what you want to do then is trace the line back to the focal length. So that's the first one. The second one you do is you pretend like this light, if there was no lens there, this ray of light would go towards and through the focal length on that side. But because the lens is in the way and it's going to refract that light, it will go that way to there, but oh no, can't get to the focal length. And because it was headed towards the focal length, that same idea applies of parallel lines in the focal length. This will come out parallel. Now we trace that back. You can see these are diverging. They're never going to come together. And so we trace that back. and we get an image on the same side and right side up as the object itself. And so looking at this diagram, this rough diagram, I go, my math should tell me that the image is smaller than the object and that it's within the focal. The image shows up within the focal length here. So let's hope that's the case. So 1 over f equals 1 over do plus 1 over di. And we'll put in the numbers then. 1 over 2 centimeters equals 1 over 6 centimeters plus, oh, it should be -2. Sorry about that. That's a mistake that you'll lose marks on in your test. So -2, that was important. And we don't know the image distance here. So we got that, and that's key to this, because if you remember from the last example, that if the image shows up on the same side of the lens as the object, then we expect a negative number for our DI. So I didn't have a negative number there. We would not get what we expect. So we have this, and this. So same as before, subtract off your fraction on this side. What you do to one side, you must do to the other. Notice this is a negative number minus a negative number, even though these are fractions. We get 1 over 2, and since the negative doesn't really matter in a fraction, so I'll just put it up there, minus 1 over 6 equals 1 over di. And in order to subtract these fractions here, we got to have a common denominator, so we want 6 on the bottom. So 2 times 3 is 6, so 1 times 3 is 3. 3 over 6 is still a half, so I'll say -3. And again, I've moved my minus sign up here because I'm dealing with the numerators here in the end. For a negative fraction, it does not matter if the numerator or denominator, or you just call the whole fraction negative, it doesn't matter. Minus 1 over 6 equals 1 over di. I get 3 minus 1 is minus 4 over 6. I don't need that 0 there, but anyway, equals 1 over di. And now we cross multiply. You'll notice there's a negative number in there, which is great because we wanted our distance to the image to be negative since it's on this side of the lens. We get minus 4 times the distance to the image. 1 times 6 is 6, which is nice. Divide out the minus 4, divide out the minus 4, which will give us a minus number for the distance to the image. And that gives us minus 1.5 centimeters, which our rough drawing here that we did matches that. That's not quite 1.5, but that was 2 centimeters, so it should be within there, and that's what we found. So again, these are handy even if you are just going to sketch them out the way I've done here. Height of image over height of object equals minus distance image over distance object, same as before. So all this is going to be exactly the same as it was earlier. We don't know HI. We know the height of the object is actually 1.5 centimeters. We know this is minus 1.5, which makes the whole thing plus, all over the object distance, which was 6. Cross multiply, we get 6 times the height of the image. 1.5 times 1.5 is 2.25. Divide out the 6, divide out the 6, and we're left with the image height is 0.375, or if we round that up to 0.4, if we're being careful here, 0.38 I'd be happy enough with in this case, centimeters as the height of the image. So just to wrap things up here, this is the last example. There's lots more to do, lots of other there's some weird scenarios too where the object is at the focal length or twice the focal length is a special point as well, but how you do these doesn't change. Also, I made a mistake in the last example where I talked about burning ants. That was not a case of where you burn ants. That's actually a case where the distance to the object is infinity, and so all the lines are parallel, and the focal length ends up being the the distance to the image, which is why you get that nice hot spot of the sun when you do that. So that was a mistake in that one. That's not that case. Solving mysteries was fine. Yeah, stamp collecting, all that stuff. That's what magnification glass. That's the example that was. So. I think that's it. Do all the practice, and I will see you after the break.